Okay, so we'll go ahead and begin lesson 2 of week 6. And the topics we're going to focus on today are this other property we're going to learn about called electronegativity. And then we're going to learn about more about covalent bonds, speaking about their polarity, so nonpolar covalent bonds versus polar covalent bonds. Then we'll learn about something called resonance structures. And we will also learn about formal charge. Okay, so electronegativity, what is it? Well, the definition is right here. The relative ability of an atom to attract electrons in a bond to itself. Relative ability of an atom to attract electrons in a bond to itself. So it's an indicator of how possessive an atom is, an element is, of the electrons in a bond in which it is involved. So electronegativity always involves an atom that's participating in a bond. So as you can see from this diagram here, there is a periodic trend, and that trend is, and that electronegativity increases as you go up and to the right on the periodic table. And in this particular property, we're leaving out the noble gases because the noble gases are considered to have really no electronegativity at all because they have that noble gas configuration, which means they're happy with their electron configuration. They don't really need to possess electrons in a bond. And most of the noble gases don't even engage in bonding. So the most electronegative element is fluorine, and these are arbitrary values. So it was Linus Pauling who developed this scale. He's a famous chemist from the 20th century. And so it's an arbitrary scale, and it was developed so that fluorine is the most electronegative element, which was assigned a value of 4, an electronegativity value of 4. And the least electronegative element is francium down here in the lower left-hand corner of the periodic table. And so it was given a value of 0.7, and cesium also 0.7. So this is all relative, and then everything else is in between. Okay, so once again, if you have two atoms in a bond, the one that possesses the electron pair more than the other would be more electronegative. Okay, so that can lead to, whenever you have a bond between two atoms, that bond can have polarity. It can be a polar covalent bond. So let's talk a little bit about that.
Mine.
Okay, so if you remember that movie Finding Nemo, right? That the sound effect there, the seagulls, they're very possessive, right? Those any kind of food that found its way into their environment, they were very possessive of it. Well, that's kind of what we mean by electronegativity, but it's with electron density. So over here in this picture, if you have two atoms of the same type in a bond, so that's there's a bond between these two hydrogen atoms, and this oval right here represents the electron cloud, that electron pair that's shared between the two hydrogen atoms. So since they're exactly the same element, one is not going to possess the electron pair more than the other. It's going to be the same. So we can call that equal sharing. Okay, so equal sharing. Okay, but down here, the fluorine, we said, is more electronegative than hydrogen. So it wants that electron pair more than the hydrogen. So that's why it's shaded darker towards the fluorine, and the lobe is a little larger on the fluorine side than it is on the hydrogen side, a little lighter, a little smaller. And that's because the electron density is not shared equally. It's unequally shared, and it's skewed towards the more electronegative element, which is the fluorine. So this is unequal sharing. Okay, and so that's why this is a polar bond, and where there is no electronegativity difference, that's going to lead to a non-polar bond. Okay, so it results in an uneven distribution of charge. So remember, because electrons have charge, and so if one side of the bond has more electron density than the other, then the side that has more electron density will have a partial negative charge, okay? And then the other side, by default, will have a partial positive charge. So that's what we mean by an uneven distribution of charge. And you can see it in this picture right here, how the negative charge of the electrons is kind of unevenly skewed towards the fluorine side because fluorine is more electronegative. Okay, and also you could say that, remember that in an ionic bond, you have a complete transfer. So in an ionic bond, all of the electron density from one atom would be donated to the other, or at least of an electron. One electron would completely go. from one atom to the other. So that would be an ionic bond. And so the more polar the bond, you could also say that it has more ionic character. So the more polar the bond, the more ionic character it has. Okay, so how do you know how polar a bond is going to be? Well, that's where you have to calculate something called a difference in electronegativity. So you use those values of electronegativity, which were in the couple slides ago, and you can just subtract the two numbers for the two atoms involved in the bond, and based on that electronegativity difference, you can determine what type of bond it's going to be. If it's going to be a non-polar bond, or it's going to be a polar bond, or if it's going to be an ionic bond. And so what you need to put in your handout is this information in the red box down here. So if you were to go, so just let's say, for example, this molecule right here, F2. So these are both fluorine atoms. All right. Well, whatever the electronegativity value for fluorine is, the other fluorine is going to have the same electronegativity. So that difference in electronegativity would be 0. So even though it's a very electronegative element, the difference is what matters. The difference in electronegativity is 0. And so we would call that a non-polar bond. Okay, so now let's look at a different compound here. This is HF, the HF molecule, hydrofluoric acid molecule. So in this case, the fluorine is more electronegative than the other atom involved. This is the hydrogen. Okay, so this perhaps isn't super obvious, but this is the fluorine in this molecule, and this is the hydrogen. Okay, and so the fluorine's electronegativity value is 4. If you were to look up the electronegativity value of hydrogen from that table, you would see it's 2.1. And so the difference is 1.9. And so anything in that range of 0.4 to 2, electronegativity difference of 0.4 to 2, this is what we would call polar covalent. So this whole range is polar covalent. Okay, this range right here, okay, that's the non-polar covalent. So it doesn't have to be exactly the same element, but as long as that difference is something less than 0.4, we consider that to be a non-polar bond. But then if you get bigger than the difference of 2, okay, that's just considered an ionic bond. That difference in electronegativity is so big that you might as well say that you've completely transferred the electron from one to the other. So like it is in lithium fluoride. So here's your fluoride ion now, because it's completely accepted that electron from the lithium +1 ion. Okay. Now again, these are kind of gray areas. You'll see different. If you look up different textbooks, you'll see that those demarcations are sometimes different. But the idea is that it's in this range of 0.4 or in this range of 2.0. There are some bonds that have an electronegativity difference of around 2.0, and they're still considered one or the other, and the same thing on the other end of the spectrum here. But the big deal here is, you can get a pretty good idea about whether the bond is going to be non-polar, polar, or ionic based on that electronegativity difference. Okay, so just a couple ways to indicate the bond polarity. So one way to do it is with these are lowercase Greek letter delta. Okay, that's what it looks like. And the way you would say that is a partial positive charge, a partial negative charge. So it's not a full positive, it's not a full negative charge. It's not a complete electron one way or the other, a loss of one electron or a gain of one electron. So they indicate that with like this. And so you would see it represented in a Lewis structure like this. So the hydrogen is less electronegative. So it's going to be the one that has the partial positive charge. In this polar bond, the chlorine is the more electronegative element. So it possesses the electrons of this bonding pair unequally. So it's going to have a partial negative charge. Okay? So that's one way to show it. The other way to show it is with an arrow. You'll see it like this. So this type of notation shows you the bond polarity, okay, because the arrow points towards the negative end. So the arrow pointing towards the more negative end of the bond. And then, they kind of make it even more obvious by making the other end of the arrow something that looks kind of like a positive, a plus sign, right? So this would be the positive end of the bond. This would be the negative end of the bond. partial positive, partial negative. Okay, so just a couple different ways to represent the bond polarity. And of course, as we already talked about, there's a magnitude of polarity here. This, what we call a dipole moment. I should probably write that down. So you may want to add this to your notes. So this sets up what we call a dipole moment. A dipole moment, and that's just a measure of how polar the bond is. Okay, and it's based on that electronegativity difference. Okay, so let me do another example here, or let me do an example here. So we're told to draw the Lewis structure for carbon, hydrogen, fluorine, chlorine, bromine, and then decide which bond is the most polar, okay? So carbon has, remember the rules for doing Lewis structures. I have one of each of these elements, one carbon, one hydrogen, one fluorine, one chlorine, one bromine. So the way in which we're going to choose the element, the atom that goes in the middle, is the one with the largest bonding capacity. Carbon has a bonding capacity of 4. All the others just have a bonding capacity of 1. These are 3 halogens, right? These are in group 17. And then hydrogen, which has a bonding capacity of 1. So I'm going to put carbon in the middle, and I'm just going to put the other elements around it. Okay. And I'm just going to kind of cut to the chase here. So if you do the process that we went over in lesson 1, you would get this Lewis structure. Okay, and of course we have lone pairs around these halogens to give them their octet. And hydrogen does not have that because it's happy with just the 2 electrons. So the question says, which bond is the most polar? Well, so that's going to be based on the difference in electronegativity between carbon and whatever else it's bound to. And so you don't even need to know the electronegativity values to answer this question, because you can just use the periodic trend. Okay, you can just use the periodic trend to kind of answer the question. So fluorine is the most electronegative. So that fluorine is the most electronegative. Capital E, capital N is often used as an abbreviation for electronegativity. So that means that this electronegativity difference is going to be the biggest, right? So this is going to be the biggest electronegativity difference. And so that means that bond right there is going to be the most polar. Okay, so if you were to do the electronegativity differences here and here, you would see that these would be polar bonds. All 3 of these bonds would be polar. If you do the electronegativity difference here between carbon and hydrogen, it's pretty small. So this bond right here is considered nonpolar. And you'll talk about that a lot in organic chemistry. If in this course, a little bit later in this course too, but in organic chemistry, you'll get into that if you have to take that course. But the other 3 bonds are polar, but the most polar one is the carbon-fluorine bond, because that's got the biggest electronegativity difference. Okay, so once again, Lewis structure, just to make things a little simpler, I didn't put the lone pairs on there. And then that one is going to be the most polar bond because it has the largest electronegativity difference. Okay, so our next discussion is about this thing called resonance structures. Resonance structures are defined as when you can draw 2 or more Lewis structures with the same arrangement of atoms, but a different arrangement of bonding pairs of electrons. So all the atoms are in the same place in 2 or more structures, but the bonding pairs of electrons look different. 2 or more Lewis structures with the same arrangement of atoms, but different arrangement of bonding pairs of electrons. So for example, first of all, this only occurs, you will only find resonance structures when you have molecules that have double or triple bonds. Okay, so here's an example. So ozone, this is the molecule that's in the upper layers of the atmosphere that blocks a lot of the dangerous UV radiation coming from the sun. And so you can draw 2 equivalent resonance structures. Okay, so if you do the Lewis structure for O3, you have to put a double bond in there. Well, in this structure, this Lewis structure on the left, we put the double bond between the 2 oxygens on the left. Well, why did we do it? There's nothing saying that we can't draw the double bond instead between the 2 oxygens on the right, as is shown over here. So those are 2 equivalent Lewis structures. One is not really different than the other in terms of the position of the atoms. All the oxygens are in the same place. What's different about it is the arrangement of bonding pairs. Here we have the bonding pair, the double bond, pardon me, here we have the double bond between these two oxygen. Here we have the double bond between two different oxygen atoms. Okay, so what actually happens is neither of these are the correct structure, the structure that you actually find in nature. And we'll get into the reason why next week. But really what happens is they kind of mix together. So the actual structure is an even mixture of the resonance structures. And the way you know that is because if you go into the laboratory and you measure that bond length between the oxygens, they're the same. It's 128 over here and 128 over here. And we'll learn in lesson 3 that typically speaking, double bonds are shorter than single bonds. So we're kind of jumping the gun here a little bit, but it's necessary to understand what we mean about resonance, what we want to know about resonance structures. Double bonds are typically shorter than single bonds, but when we actually measure this molecule's bond lengths, the bond lengths are the same. So what that means is it's not this structure and it's not this structure, it's some sort of mix between the two. But this is the way we kind of have to represent it in order for us to really do an accounting of where all the electrons live. Okay? All right, so that's what we mean by resonance structures. Now, another one that you often see is in this molecule we call benzene. Okay, and you'll see this a lot in organic compounds. So it doesn't have to be benzene, but the key is that benzene is a great example of when in organic compounds, when you have a lot of carbon atoms connected together, sometimes they set up this arrangement where there's this alternating pattern of single and double bonds. And benzene has that. So alternating single and double bonds. So you can see that in the picture. This is in your handout. And so this is the structure of benzene. It's C6H6. So 6 carbons, 6 hydrogens. And there's that pattern of single bond, double bond, single bond, double bond, single bond, double bond. Okay, well, so the question is, well, why did I start with a single bond and then do the double bond? Why couldn't I start with a double bond and then do the single bond? Well, you can, okay? These are resonance structures. They are equivalent. The atoms are in the same place. It's just the bonding pairs have been rearranged and they're still legitimate, okay? So one way that's often used to represent this, just to kind of indicate the idea that you do have resonance structures there, is instead of drawing it discretely like a single bond, double bond, single bond, double bond, is they just put a circle in the middle. Okay, and that has special meaning that you'll get to in organic chemistry as well. It's called aromaticity, but I won't get into that today. So the circle indicates a uniform distribution of electrons. And again, what we see if you measure the bond lengths in between these carbons is they are all the same. The bond length between these two carbons is not shorter than the bond length between these two carbons. They are all the same bond length. So that means, once again, that it really is not one or the other, but it's kind of like both at the same time. It's a mixture of the two. Okay, so that's benzene. Just a couple more examples, and these aren't in your handouts, just to show you more examples. So the nitrate polyatomic anion, if you were to draw the Lewis structure, you'd have to put a double bond between the nitrogen and one oxygen. Well, why do I have to put it between the nitrogen and the oxygen up top? Could I put it between the nitrogen and the oxygen on the left? Well, yeah. Could I put it between the nitrogen and the oxygen on the right? Well, yeah. Okay, so you can see that it's like this double bond can flip places from here to here to here. All right, so those are 3 different resonance structures. Okay, and here's another example of a benzene-like molecule that has resonance structures, and this is naphthalene. And so, if you can imagine the smell of mothballs, right? Mothballs are naphthalene. This is the compound that is responsible for that smell, and that keeps the moths out of when you're storing your clothes and things like that, old clothes. Okay, so there's just more examples of resonance structures in compounds. Okay, so the next topic we want to move on to is formal charge. So what is it? Formal charge is a way to do some more accounting. It's for accounting purposes. So it's defined as the formal charge of an atom in a molecule is the hypothetical charge the atom would have if we could redistribute the electrons in the bond evenly between the atoms. Okay, so it's a hypothetical charge. It's not real. It's just kind of a method of accounting. The hypothetical charge of an atom would have if we could redistribute the electrons in the bonds evenly between the atoms. So this picture right here kind of illustrates what we're talking about. This is CH4 methane. And so each one of these bonds, that's why it's color coded. You got a red side and a blue side. That's going to indicate, all right, we know that 2 electrons are in this bond. Well, what if we gave one of those electrons to each atom? We gave one of those electrons to each atom. Same thing for each of those bonds. Okay, so then the question is, well, if I did that, would any of these atoms have an actual charge? Would they be positively charged or negatively charged, or will they be neutral? Okay, well, the way to figure that out is, first of all, you just think about their Lewis symbol from, like we learned in lesson 1, the Lewis symbol. Is this any different than the Lewis symbol for that element? If yes, then there is a formal charge. If no, then the formal charge is 0. But there's an equation that you can always use to calculate it, and this equation is on your equation sheet. So to calculate the formal charge, all you need to know is, first of all, the number of valence electrons that are usually present in that element. And then you subtract from that a summation. That's what the brackets are for. You got to add a couple things together before you subtract it from the number of valence electrons. You're going to add up the number of lone pair electrons that you see on that atom, and then you're going to add to that 1/2 of the bonding pair electrons on that atom. Or the other way to think about this is the same thing as the number of bonds. Okay, so whichever way makes most sense to you, 1/2 of the bonding pair electrons, or if you just want to add to the number of lone pair electrons the number of bonds that it has, then you get the same answer. Okay, so let's do an example. So N3-, this is a polyatomic anion called azide. And as you can see here, the first thing we need to do is, in any time you're going to do a calculation of formal charge, if you're not given the Lewis structure, you're going to need to draw the Lewis structure. So remember our process for determining the Lewis structure. The first thing I need to figure out the total number of valence electrons in N3-. Well, there are 5 valence electrons in each nitrogen, and I have 3 of those, but then I have an extra electron from the negative charge, so that's 16, okay? And so then I can just put the 3 nitrogens, and I don't really have to worry about which one goes in the middle because they're all the same. There's 3 nitrogens, so I'll put a nitrogen in the middle, and then I put the other 2 nitrogens around it. And so I got to use up all 16 of these electrons somewhere, so I'll start by just connecting the atoms together. So that uses up 2, 4, so -4 gives me 12 electrons. And so if you remember your step-by-steps, the next thing to do is to give the perimeter atoms their octet with lone pairs. Okay, so I just did that, and so I used up 2, 4, 6, 8, 10, 12. So I used up the rest of my electrons to do that. So then the question is, well, does everybody have their octet? Well, this nitrogen does, 2, 4, 6, 8. This nitrogen does, 2, 4, 6, 8. But this nitrogen in the middle does not have its octet. It has 2, it has 4. So remember the way in which I deal with that, and there's a couple ways to do it. But I'm just going to show you one way, and then we'll get into the more nuanced part of it in the next example. But what we can do, remember, is to take lone pairs on an adjacent atom and convert them into a bonding pair. So what you end up with is nitrogen, double bond, nitrogen, double bond, nitrogen, where these guys on the ends have 2 lone pairs, and then that whole thing is a negative ion. Okay, so that is the Lewis structure of azide. Okay, that's what you need first in order to calculate formal charge. So I'm going to erase all that, and then we will let PowerPoint take over from there. Okay, so 16 valence electrons total in N3-. So one thing that's going to be important is to distinguish the different nitrogens. You are going to use subscripts, and so in this case, I just use subscripts A, B, and C. This is not like sodium. This is not Na as in sodium. This is N for nitrogen with the subscript A. And same thing, this is not niobium. This is nitrogen with the subscript B. Okay, so assigning all of the electrons, we get a Lewis structure with double bonds in it. Okay, and so there's our Lewis structure. And so now we'll take it from there to start calculating formal charges. All right, this is an ion. Okay, so now what we're going to do is we're going to apply this equation to each one of these nitrogens. So the formal charge for nitrogen A, okay, is going to be the number of valence electrons, which this is going to be, nitrogen always has 5 valence electrons. So NVE for nitrogen A is 5. The lone pair electrons, as you can see, are 4. 1, 2, 3, 4. That's lone pair electrons. And then 1/2 of the bonding pair electrons is 2. Or like I said, you can just count the number of bonds. So 1, 2. Or there's 2 electrons there, 4 electrons total. 1/2 of 4 is 2. Okay, so now you can, let's do the same thing for B and C, and then over here we'll throw another column up on the screen here that actually calculates the formal charge by using this equation for each one of those nitrogens. So for nitrogen B, we have still 5 valence electrons. I don't have any lone pair electrons on B, and I have 4 bonds. 1, 2, 3, 4. So 5, 0, 4. And nitrogen C is equivalent to nitrogen A, so 5, 4, 2. Okay, so now we have all the numbers that we need. We have the NVE, we have the lone pair electrons, we have the 1/2 of the bonding pair electrons. So I have that for each one of these nitrogens. So now I can calculate the formal charge for each of these nitrogens. And it turns out to be -1 for nitrogen A, +1 for nitrogen B, and -1 for nitrogen C. All right? So a way to represent that in your Lewis structure is with a charge that's enclosed in a circle. So the -1 would be a minus sign in a circle. +1 plus sign in a circle. Same thing with the minus on nitrogen C. Okay, so here's an interesting thing, or an important thing to remember, that your formal charges always have to add up to the total charge on that molecule or ion. Okay, so since this is a -1 ion, these formal charges better add up to -1. Well, -1 + 1 -1 does add up to -1. So the sum of the formal charges must equal the overall charge. Okay? All right, so that's how you calculate formal charges. It's how you use the equation and how you apply it. All right, so let's do another example here. And this one is also going to lead us into, this shows us the overlap between resonance structures and formal charge. So here's our formula, N2O. And so just ask the question, well, hey, let's just draw the Lewis structure for that and calculate the formal charge on each atom. Okay, so, and we're told that the position of the atoms is this: nitrogen, nitrogen, oxygen. Okay, so first of all, remember that in order to do a Lewis structure, I want to figure out the number of valence electrons for the whole chemical formula. So that's 5 for each nitrogen, so it's 5 times 2. And then we have oxygen, which is 6. So that's a total of 16 electrons that we have to assign. So if my positions are here, nitrogen, nitrogen, oxygen. So I'm going to put those, I'm going to connect those together with bonds. So that uses up 4. Okay. So now I've got 12 left. And so remember, what you should do next is to give the perimeter atoms their octet with lone pairs. Okay. So I did that, and that used up 12 more electrons. So 2, 4, 6, 8, 10, 12. So I've used up all my electrons. Well, once again, my nitrogen in the middle does not have its octet. So I need to change some of these lone pairs on adjacent atoms into double bonds or multiple bonds to give us an octet on every atom in the structure. Okay, so there's a couple ways to do that, I guess is one way to say it. So what we saw on the previous slide was, well, we used a lone pair on one atom and made it into a double bond. We used a lone pair on another atom and made it into a double bond. And so that transforms then into something like this, where you have nitrogen with 2 lone pairs, double bond, nitrogen in the middle, double bond, oxygen with 2 lone pairs. Okay, so that's one possible Lewis structure. But that's something else I could have done is instead of having a lone pair on 2 different atoms form a multiple bond, I could have done something like this, where I just use 2 lone pairs on the same atom to form a triple bond. Okay, so another way I could have done that is, you know what, I'm just going to redraw this so that you can see more clearly what I'm talking about. So we have the nitrogen. Okay, so in this case, what I'm going to do is I'm going to have 2 of the lone pairs on this nitrogen to transform into a multiple bond here with this nitrogen. And so what that's going to result in is a triple bond between the 2 nitrogens, and then we have the single bond with the oxygen. Okay, Well, the other way that I could do it, back again to my original Lewis structure. I could essentially do the same thing with the oxygen. I could have these lone pairs on the oxygen transform into multiple bonds with this nitrogen. So that would result in a nitrogen and a triple bond with the oxygen. Okay. And it still has one lone pair on it. Okay. So now if I wanted to calculate formal charge, you could do that for these three different Lewis structures. I could calculate the formal charge on each one of these nitrogens and the oxygen for these Lewis structures. And so I'm going to let PowerPoint take over from there. Right. So I'll erase all that. So there are three possible Lewis structures, and the question really is, which one is the best Lewis structure? And so that's where I'm saying that this is where we enter that overlap between the idea of resonance structures and the idea of formal charges, because the best one is going to be dependent upon the formal charges that we have. So you could have this Lewis structure that I drew out, or the one with the two double bonds, or the one where you have the triple bond with the oxygen. Okay, so now we need to apply the equation for formal charge and calculate the formal charge on each one of these atoms in each one of these Lewis structures. Okay, but before we do that, let's review the rules that are going to tell us which one is the best, which one is the most stable, which one is the Lewis structure that closest resembles what we actually see in this molecule. So first of all, the Lewis structure that has all formal charges equal to 0 is going to be the best one, or as close as possible. So if two of the three, or one of, if you want as many formal charges to equal 0 as possible. That's one thing you definitely want to look for. All right. So the next rule is, let's say that you can't get all the formal charges to 0, and you end up having to put a negative formal charge on something. Well, you want to pick the one where you put the negative formal charge on the most electronegative element, or the more electronegative element. Okay, so for example, these are the three Lewis structures that I just generated right here. And so in your handout, you don't have rows 1, 2, and 3. You just have row 4 here, but that's really all that matters. These rows 1, 2, 3 just kind of show you how the numbers that are in row 4, the formal charges, were calculated. Remember that the formal charge is the number of valence electrons minus that sum of the lone pair electrons plus 1/2 of the bonding pair electrons, or the shared electrons. Shared electrons, bonding pair electrons, same thing. And so if you apply that equation to the different numbers for each of these structures, okay, then you get this. You get, in this structure over here, this nitrogen has a formal charge of 0, the middle nitrogen is +1, and the oxygen is -1. The one in the middle here, the nitrogen's -1, the nitrogen in the middle is +1, and the oxygen is 0. Okay, and over here it's -2 on the nitrogen, +1 on the nitrogen in the middle, and +1 on the oxygen. Okay, so now that you have all those formal charges calculated and written down, you can evaluate each one of these Lewis structures based on this criteria that we just laid out. So first of all, the first rule says we want to minimize the formal charges. We want to get all the formal charges as close to 0 as possible. So that's why we can just kind of eliminate this one from contention, because none of these formal charges are 0. And at least on the other two options, I've got at 1, 0. I've got a 0 in these two. But this guy here has no zeros. So eliminate that one from contention. This is not really the structure that this molecule adopts. Okay, so now the question is, well, each of these have a 0, and they each have a minus. So that's how you're going to make the call. So remember the second rule here. The negative formal charge needs to go on the more electronegative element. Or remember the periodic trend. Electronegativity increases as you go up and to the right on the periodic table. Well, oxygen is further to the right on the periodic table than nitrogen. So oxygen is more electronegative. So you want to pick the one where the negative formal charge is on oxygen. Here the formal charge is 0 on oxygen. Here the negative formal charge is on oxygen. Over in this one, the negative formal charge is on nitrogen, which is less electronegative than oxygen is. So again, following the second rule, we can eliminate this one from contention. And then by process of elimination,
yes, indeed,
this is the Lewis structure that is the best, or the most stable, or the one that best represents what you actually find in this compound. Okay, So resonance structures, they are equivalent in terms of their position of their atoms, but they're different in terms of the arrangement of the bonds. But that doesn't mean that all resonance structures are the same in terms of their actual representation of what we really find in nature or out there with the, in the real world with the compound. Okay. And so once again, just to remind you that, even though you might come up with formal charges on these atoms, like you see here, that depends on the Lewis structure that you draw. And so it really is a mixture. It's not like this oxygen has a -1 formal charge and this oxygen has a -1 formal charge. Because of the different resonance structures, it really is just a mixture of all of the potential resonance structures. And so what you end up with in this case is, the equivalent bond lengths, that's true, but you also have equivalent amount of charge. It's not like you have 2 oxygens with charge and 1 oxygen without charge. All 3 of the oxygens have the same amount of negative charge, but it's just been smoothed out over all 3 of the oxygens. Okay, so instead of formally -1 and -1 and 0, you have formally -2/3 partial negative charge on all the oxygens. So in reality, the true structure of the molecule or the ion is a mixture of all possible resonance structures. Okay. All right, so we'll stop there. And what we learned about today should enable you to do questions 6 through 13 in your homework assignment. And then from the extra practice, you should be able to do 26 through 44. And then some good tutorial videos from Professor Dave, Crash Course Chemistry, Bozeman Science, and the Chemistry Solution. The one on Chemistry Solution is actually really good. If you were to pick one, I would pick this one from Chemistry Solution to watch. All right, thank you very much.